Hello and welcome to today's video. Today I would like to introduce the Wyoming Infrared Telescope, WIRO. As always in this series, I will first talk a little bit about history and purpose, motivation of the telescope or the observatory, then shortly about the equipment and geography, and then also present some results, which is especially easy in this telescope because all the papers are listed on the web page, and then give a short summary outlook, which is rather speculative because I don't know about the newest history of this observatory. For the history, I more or less rely on a video that can also be found in the internet by Bob Geertz, and Bob Geertz was one of the founder fathers of this observatory, and the video and especially this story is very impressive. I think they had the plan to set up an observatory and also had some people that could teach them about earlier techniques in infrared observatories, for example from the Kitt Peak and from the University of Minnesota. And these guys built a lot themselves, for example microbolometer detectors, which I find very impressive because it involves soldering under the microscope, which is quite something, I think. And after quite a long story, first they wanted to go to Hawaii to set up the observatory there, and then thought it's just too expensive, not only paying for the observatory but also paying for using it later. So somebody gave them a hint for a mountain. We'll show you later where it is exactly, and they were very lucky because on the mountain there was a fire tower and an electricity line going up there, and they could more or less buy the building for $1 and then start building on the mountain. But the road had to be widened and the peak flattened, which took a lot of work. And then they built some water tanks first, because on the top of the mountain, of course, you don't have any water. And they built a little house to live in, also where the control room is, and then the observatory. And the astronomers had to learn to drive a snowcat for the winter. And then the mirror was made in Arizona, and another company made the mount. And installing the frame mount with a crane was really quite something on this little mountain, with a crane and lorries that were not able to turn around on the mountain, so they had to be turned by the crane. The original aims, I don't know exactly, but some of the aims were to look at stars, for example runaway stars that are shot out from their environment, to look at massive binaries and also at blazars. And they could observe, in the beginning, they could observe dust formation in Wolf-Rayet star, UV Scuti, and they also discovered a new globular cluster, which is also nice. And here, as you can see on the image, they could make a picture in the infrared from the collision of comet Shoemaker-Levy 9 with Jupiter. Actually, they wrote it wrongly here on the image. It's Shoemaker with OE, I think. The equipment is a 2.3 meter telescope, which is a classical Cassegrain with a movable 8-inch secondary mirror. The movable mirror makes it possible to have a control measurement. If you're looking at something, you can look away from this something and then build the difference. And the mount is quite similar to the large Mount Palomar telescope with a large frame, and the telescope is inside the frame. And they say it can be moved with a 0.1 PS electric motor, so the equilibrium is very, very well done. And they have various detectors to see different parts of the light. A CCD camera with 2084 times 2084 pixels, which for these days is not too many. And they also have various spectrometers and a polarimeter, and of course their bolometric sensors they built themselves. For the geography, it is at Mount Jelm, which is close to Laramie in Wyoming. Not many people know about the state of Wyoming, but if you tell you that actually the Yellowstone National Park is in Wyoming, that's why most people still know what the landscape looks there. If you look at Google Map on a larger map, you can see that the Cordilleras in North America have two chains. And the chain close to the ocean is a bit higher, I think. And then there's a second chain that is relatively far away from the first chain. And these, as in the South American Cordilleras, the rain is coming down west to the first chain. And then the air gets drier and drier. That's why you have dry air here, despite being 41 degrees north, which is more or less in the west wind zone. But the west wind doesn't bring much rain because the rain has lots of time to rain out before the mountains start. And the height is 2,900 meters, which is still possible to work there properly for human beings, but already most of the atmosphere, or a lot of the atmosphere is below this point. Another thing is always the seeing. I don't know how good the seeing is, but it's not so important if you go to longer wavelength infrared. Then I can cite a little bit from the papers that I found. I didn't look at all the papers because there were 150 papers on this webpage, but I tried to sample papers from different areas. One is star formation, and there are papers from 1982 and from 1981, and they are from the founders. Grastalen we found in another video I made on another observatory, and Heckwell and Geertz are the two founders of the observatory, so they also worked there quite a bit. And they looked at 20 micron and 10 micron emissions from different parts of the sky and plotted them in this map-like manner with the curves here around the peaks. It almost looks like a geographical sketch. So they were interested in star formation. And what they also did is to monitor objects in the visible part of the spectrum, or partly also in the infrared, that were discovered in other parts of the spectrum, like X-rays, for example, or UV, and helped to compare the emission across the wide parts of the spectrum. So there were very old papers that did this, and also there are quite new papers that I tried to include only papers that mention that the telescope from this observatory was used. And they also looked at active galaxies like quasars and monitored a lot of active galactic nucleus, for example, in hydrogen beta. As you can see here, there is a spectrum, but the spectrum goes across parts of the visible and not into infrared. Then they started working with exoplanets, but more with other telescopes than with their own telescope here close to Laramie. But one paper they did here in this observatory used multicolor broadband photometry. So the idea is that you're measuring the size of a planet in different wavelengths. I mean, you estimate it. Probably you can't measure it directly, but you estimate the size. And the filters they used here are the ones sold by Bader that go from ultraviolet into near infrared. But as you can see, the filters go till not further than 1100 nanometers. So what comes through there can be measured with a conventional CCD camera. And using broadband helps to have enough light. So there was this paper by Casper and et al. That demonstrated this technique in a planet around the star Henry Draper 189733. The planets then are called B. A is the star and B is the planet. And this planet is relatively easy to see because it's very large compared to its mother star. It has a bit more mass than Jupiter, but the star is smaller than the Sun. The problem with these stars is that they have large spots. So you have to correct for that, for these star spots, when you want to say something about the brightness. I don't know if there were papers later that used the same method, but it worked for this planet around this star. So, as a summary, observations were made in the visible range and also in long-wave infrared, probably using these bolometers. I don't know if they could use more modern long-wave infrared detectors that use much more of the light. They made spectroscopy, but mainly in the visible, as I've seen in the papers I sampled. I didn't, as I told you, I didn't read all of them, just half a dozen papers or so. Some I kicked out because I've seen that they were data were collected with other telescopes and not with this one. They made impressive international collaborations, and it probably also helped that the telescope is relatively easy to book. They said, write a short email with your plan and then we'll give you the time. Sounds quite easygoing, but it's mainly used from students or members of the local university in Laramie. And of course they widened and deepened the knowledge about infrared, which is very good, and collaborations with other universities. Then I tried to look at how many from their webpage how many papers they published, and always made 10-year spins, and then in the 80s they had 45 papers, and in the 90s 28, and in the 0 years 16, and then it rises again. But I think in the newer time they also mention a lot of papers that were not based on data collected with this telescope. In the modern era, most papers are in the exoplanets field, which seems to be an interest of the professors now there. Of course, the founder fathers are not actively working anymore. They also used satellite telescopes like TESS. And for me to research was very good that they have a very open information policy and everything is listed somewhere, and this video helped a lot. And what I also found very special was the cost management during building. They did lots themselves and helped a lot, and the costs were very low. I think 60% was paid by the university and 40% was paid by the National Science Foundation, but it wasn't a big amount of money that they used for this telescope. And this is another view from an airplane or a drone on the telescope, and here you can see a little house where astronomers can live. And I also have a little garage for the cars or snowmobiles, and here the cupola of the telescope. Now that was the presentation about this WIRO observatory. Thanks a lot for the attention.